Hello everyone. In this lecture we are going to learn about design of bellows expansion joints. Our flagship courses are Master Static Equipment Design and PVElite, ASME Section 8 Division 2, and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs. So do visit our learning platform for more details. On scootoid.thinkific.com. We're excited to bring you a comprehensive, one-day workshop on Bellowdesign that dives deep into critical aspects of designing both thin and thick bellows. Register now, with the link in the description below.
So design of bellows. What are the different names which we have for bellow? Flexible shell element, expansion joint. Very rarely we call it as a spring, but you can call that. It's kind of spring. Okay. So all the different names, thick bellow, thin bellow. Yeah, great. Okay. So these are the different names for bellows. Now let us first see why we need bellows. Why you need bellows in heat exchanger. First tackle that, and then we'll see what are the methods. And so the reason is thermal expansion. Okay. Now, how will tell you? Okay, we'll be realizing with the figure. So let us see. I have a case where my YouTube is at mean metal temperature of 200 degrees Celsius, and my shell is at 150 degrees Celsius. Okay. So these are the mean metal temperatures we are talking about. So there is a difference. Okay. Consider the material is same. What will happen in this case? When tube both sides it's connected with tube sheet. Shell is also connected, welded with that tube sheet. Shell will expand with a lower length because it is at only 150 degrees Celsius, while tubes will try to expand more. So do you see differential thermal expansion happening here? Yes. So there will be differential because tubes want to expand more because of high temperature and shell wants to expand less. So think about tube sheet. Wherever shell is connected with the tube sheet, there it will try to hold the tube sheet, while tubes will be pushing the tube sheet, right? So what type of stress will be generated in the tubes? Whether it will be tensile stresses generating in the tubes or it will be compressive. Bending will happen because of what? Because of compressive stresses. Okay. So if it's very thin, okay, L by R ratio, if it's very cylinder, then it may buckle. So bending will happen. But the nature of the stress will be compressive. Right? Nature of the stress will be compressive. Okay. Why? Because tube sheet is stopping it. It is not allowing it to expand, but it wants to expand. So there will be compressive stresses getting generated. Okay. I'll show you some figures which may clarify it further. So tubes want to expand while shell is holding it. Okay. Then what will happen? First of all, if it is not an expansion joint, the complete load will be coming on the tube to tube sheet joint. Okay. If that is strong enough, then the tubes will try to push the tube sheet. Shell will try to hold it. So what kind of phenomena will occur? We can visualize by this image. Okay. The black lines are tubes. You can see that. So shell is trying to prevent, but tubes are pushing the tube sheet. So you can see the deformation happening in the tube. So if those kind of stresses are there, if the temperature difference is not much, you will be able to design the tube sheet joint for that load. But if the metal temperature is huge, the difference is huge, then does not matter how much thickness you provide of the tube sheet, it will fail. Okay. You'll reach at a point when you are designing a fixed tube sheet, you're not able to qualify. Okay. So that time you have to understand that I have to introduce a bellow, because thermal stresses are very tricky. You cannot tackle them by providing the higher thicknesses. Only one thing which you can do for tackling the thermal expansion or thermal stresses. And what is that? Let it expand. So only one thing which you can do, let it expand. Okay. So okay, that is what we do. Okay. And solution is to provide bellows. If we provide bellows are flexible shell elements. They are flexible. So if it is flexible, it will be able to take the thermal expansion. Okay. But is that bellow is only solution, or we can do something else? Is it that bellow are the only solution to tackle the thermal expansion? No. Floating heads. Also, YouTube tackles your thermal expansion. There is no thermal expansion problem in YouTube. Okay. So that is another solution. So either I can have a floating heat exchanger, or if it is possible for that uh, fixed tube sheet design, if I can change to YouTube, I can do that also. Okay. So normally oil and gas industry or any critical industry will not prefer bellow design. Why? Why normally in oil and gas or any services which are critical, very high pressure, we not prefer bellow? Why? They are very much prone to failure. Okay. So they are prone to failure, right? So it is not preferred, but if you don't have any option, then you have to do it. Okay. So see, in oil and gas, if there is a failure, the replacement time, nobody wants to spare any time for that. Okay. So all the time you'll find floating types used for, whenever it is required. So yes. Now, so these are the two options to tackle that. Either you'll have a bellow in the heat exchanger, or you'll be having one of the two options, either YouTube or floating. Okay. So I hope most of you know what is why we don't have expansion issues in this. Why we don't have problem of expansion. Because so if you see in YouTube, there is a bend. Okay. And the tubes are connected to only one end, which is the tube sheet. So tubes are flexible because of the bend, and they are connected to one side. So there is no problem of relative expansion between shell and tubes. Okay. So that is how you avoid in YouTube. In floating, the inside head, the internal head, which is, the right hand side, which is we call as floating head, that is floating. It is not connected with shell. Okay. So it can move around. So it's free to expand. And that is how you don't need any bellows for that. So tubes are not restricted by baffles. Baffles are only the passing medium. They just provide the support. We don't weld tubes with baffles. Now we know why we need bellow. Okay. So if bellows are required, then what are the different types? What are the options which we have for bellows? thick bellows, thin bellows. Okay, so let us have a little bit introduction about bellows, what exactly they are. So as we shared earlier, they are the flexible elements to take care of the thermal expansion. Okay, mechanical stress are reduced because of flexibility in the element. Okay, and they are called as bellows, expansion joint, and flexible shell element. Okay, these are the names. What is this kind of bellow? What we call? Can you identify by the figure? It's a metal bellow, but it's thin type. See, both thin and thick type are metal bellow. And when we are in static equipment industry, the bellow is going to be of metallic. So very rarely you'll be having any operation which is kind of almost no pressure and only you are using for flexibility. Then you may have a flexible element made of different material. But these are all metals. Okay. So this is called thin bellow. Okay. Now, bellows are having two different types. One is thick and one is thin. So thick bellows are designed by whom? Who designs the thick bellow? Like if you see the tree of manufacturing, start with client, then there will be a manufacturer, maybe EPC coming in between. Then there will be manufacturer who is the pressure vessel manufacturer. Okay. And then there is a vendor, okay, which can supply the standard items or item like bellow or any other standard. Okay, like for dish and forming, you can hire a vendor. Okay. So the thick bellows are made by manufacturer. The vessel manufacturer makes these thick bellow. So if vessel manufacturer is making, who will be designing them? So vessel manufacturer. Okay. So that those people will be designing also. So designing and fabricating. Now here the question comes. Okay. Can we design thick bellow by design by rule? Can we design thick bellows? We'll further expand what exactly thick bellow, if you have not understood. We'll elaborate a little bit at what exactly they are. Can we design it by design by rule? Okay. So design by rule. Now, see, earlier we used to design by TEMA RCB 8. But now if you see after the 7th edition, in or 8th edition, I guess, 8th, in 9th and 10th, 9th was released in way back 2007. So in that, the design was removed and FEA is added. So that is about TEMA. Okay. TEMA, if you refer now, there is some calculation which you can, if you refer earlier edition, which is 8th edition, you'll find the complete procedure. Cobb and Slayer method is what we follow. Slayer and Cobb method, which is followed in TEMA also, but little bit modification has been done. Okay, based on plate and beam theory. So some modification has been done in Cobb and Slayer method. But now that is used, the TEMA method is used for sizing of that bellow. Okay. So the design by rule which is existing, you will be sizing that bellow and then doing FEA is mandatory. You have to do FEA to qualify. Otherwise, your report cannot be accepted. Making sense? So it's not like earlier when we used to just design by rule. We used to do for thick bellows. You have to do now FEA. Okay, it's a mandatory requirement. Okay. Now coming to Appendix 5, which you guys might have seen for thick bellow. And also there is relative clauses in division 2. But if you see in detail, there is no calculation. Okay. So calculation is not given. Only it gives some requirement, some ND requirement. And stresses, it's just saying that calculate stresses, okay, by doing analysis. Okay. So it does not cover the design by rule methods in Appendix 5. Okay. Make sense? Now the question, somebody asked that why that design by rule method was removed. So the reason was that it was not giving the accurate stresses. That stiffness calculation done by that method was not accurate. So it was giving the stiffness very high, okay, compared to what you get from the dimensions. So slowly, because earlier there was FEA tools were not that much frequently used, so we used to follow that. But nowadays it's available. Okay, so there is no reason to follow those methods. And after that, no better method came till now. So that was the reason it was removed. Okay. Making sense, guys, till here? Okay, we'll talk about temperature. First, let us talk about thin bellow. So thin bellows are designed by vendors. They are special vendors with whom we call as bellow manufacturers. So those are the people who supplies the thin bellows, and mostly the design will be done by ASME. Okay, we'll talk about the design codes also. Don't worry. So they are in Appendix 26 also it's covered. And then there is 4.19, which talks about thin bellow design. So which method to be preferred and or to be referred and which to be used, that we'll see. So thin bellow are basically manufactured by bellows manufacturer, not by the vessel manufacturer. Remember that. Okay. And now the question comes, like, when you are designing, which one to select? So now forget about the temperature. You, based on your experience, tell me what will be your logic. Like, you started that heat exchanger modeling in PVElite or compress, and you started getting the stresses in the tubes or in the shell very high. So you thought of providing bellow. What will be your first step? Whether you'll be preferring thick bellow or you'll be preferring thin bellow. So first you'll be starting with thick bellow. Okay. Why thick bellow you'll start with? It's easy to manufacture. You can manufacture at your shop. Okay. Design costs are not high as earlier, so you can outsource that FEA to vendors like us. Okay, we can do the FEA work for you, and your design will be complete. Okay, so cycle time also will be controlled, cost will be less. Okay, so and the most important part for client, the preference most of the time will be thick bellow. Thick bellows are less prone to failures. They are as thick as shell, so failure chances are very less. Okay, so it is preferred by the client. Okay. So sometimes even client may give that you have to use thick bellow only. Okay. So in that case, definitely there is no option and you have to go with thick bellows. You can provide multiple, like definitely thick bellow, the thicknesses are high, isn't it? So if thickness is high, your flexibility will be less. Your K stiffness will be more. So your deflection will be less. You are providing the bellow for deflection. So less deflection is not good. Okay. But that is what you get in thick bellows. Okay. So you can provide 2, 3 bellows. Okay. Sometimes, some companies, I'm also seen 6 or 7 thick bellows getting used, but that is very, very rare. So that is the one thing. Okay. And mostly you'll be seeing that if the differential temperature is less than 40 degrees Celsius, thick bellow you can accommodate. Okay. With it, that will be able to accommodate your thermal expansion. If your mean metal temperature difference between shell and tube If that is more than 40 or 50, then it starts becoming difficult. And then you may select a thin bellow for that. Making sense? That is based on the mean metal temperature difference. So first preference will be thick bellow, and then second will be thin, but definitely that will be subjective, and what is your application, that may decide your thing, but we can fairly say that thick will be preference and thin will be after. Is it making sense? So don't worry, I'll repeat the selection again. Okay. So because majority of the time as a designer, your intervention will be about the selection, which one to select. Stresses are not getting qualified for fixed type heat exchanger, and you have to provide a bellow. So first you will see what is my mean metal temperature difference. Mean metal temperature of tube, mean metal temperature of shell. Now, most of the time, it will be available. If it is not available, then what? What if mean metal temperature itself is not available? Does it make sense for a fixed tube sheet design that MMT is not available? You can apply the logarithmic formula to calculate, but not we consider linear relation and we calculate. Okay, so LMTD we use and calculate, yes. But see, HTRI you are already doing for designing that heat exchanger. Okay? And HTRI report, which is the input for you, they calculate mean metal temperature exactly. Okay. So if you're already doing it, why not to take from process? Okay. So if they have not given, ask. Definitely they are having that value. And fixed type heat exchanger, your mean metal temperature is the most relevant data, isn't it? Because that will decide whether bellows will be there or not. So it's very important. So selection again coming back. So if you have mean metal temperature difference less than 40 degrees Celsius, go for thick type of bellow. If the temperature difference is more than 50, and the temperature difference, I'm talking about mean metal temperature difference, okay, not the design temperature. So if that is more than 50, you may have to select a thin bellow. Okay. As a designer, our preference should be thick because that is more rigid. So client preference also may be thick. So we'll try first with thick, and then we can go with thick. Make sense? Now let us see a little bit detail, like what exactly are the thick bellows? Okay. What are the thick bellows? And what kind of different configuration we can have. So now this is flanged only type thick bellow. Now how we name it? So this portion is defined as flange. This we call as flange. The straight portion is called as flange. Okay. So this is flanged only. Okay. Here this configuration you can call it as corner. So this is flanged only. Okay. Second configuration you can have is flanged and flewed. So this is flanged and this is flewed. Here again, the configuration is kind of flanged because it's a straight face. Most of the code refer as flanged. Okay. Even in API 650, you'll the flared construction, that straight face is called as flanged. Okay. So don't think that flange means it's the flanged joint. Okay. The straight portion we calling it as a flanged. So this is flanged and this is flared. Making sense? So flaring is basically what we're calling as flewed. So flanged and flewed construction. Making sense? Yes. If yes, then this is the third construction, corner, corner. There is no round. Okay. There is no radius at both the ends. There's only corner. So we are calling it as corner, corner type of thick expansion joint. Okay. Then the last one, fluid only. There won't be any flange, only fluid, and the other will be corner. So fluid and corner. So these are the four different types of construction for thick bellows. Okay. If we talk about design, like how we design them, what are the codes which are available for design by rule? So this we discussed. SCOP and MF Sayer method is available, which was referred or used in TEMA. So this is the method which is adopted in TEMA, little bit modified. Okay. So TEMA RCB 8 already takes care of SCOP and MF Sayer method. And if you see PVElite also give you these two options for thick bellow. Okay. For some reason, they are not printing the result. I don't know why. So partial report only they are generating. I don't know why. So that is the problem of PVElite. But okay. So ACB Section 8 Division 1 Mandatory Appendix 5 also talks about thick bellow, but there is no calculation mentioned. Okay. So only some brief information about guideline that is there. And then Division 2 Part 4 4.20, which is exactly same as Mandatory Appendix 5. There is no difference. So 4.20 and then Appendix 5. Both are exactly same. So these are the design codes which you can follow. But you know that if you're doing design by rule, you have to follow up with design by analysis for thick bellows. Now, what about thin? We'll see. So let us first see what are the different configuration possible for thin type bellows. So let us see that first. So this is a thin bellow. You can see the convolutions. So it can be either single sheet or it can be multiple sheet. Okay. So it's a sheet formation. Okay. So these are made from the sheets, while the thick bellow is made from plate. So that is also a difference. So single or multi layers can be there. So this is the ply. Okay. So one sheet is one ply. Okay. So either you can have a one ply or multiply. Okay. So this is multiply. So multiple layer. Then you may have unreinforced. There is no reinforcement provided to the bellow, or you can have a reinforcement provided. So you can provide a ring kind of thing so that it will be more rigid. Okay. So reinforcement rings can be provided, or the shape itself can be toroidal. Okay. So toroidal shape you can have, that will be giving good strength than compared to normal bellow. So that also can be used in case of your application is a little bit critical, but definitely it will be much costlier than normal bellow. Now coming to design code. So what are the codes available? Mandatory Appendix 26, okay, which we use. And this covers the details in quite detail. Okay. Division 2, Part 4, 4.19, exactly is the extension of 26, because now if you see the latest code, most of the Appendix 26 portion has been moved to 4.19. Okay, so you'll find this kind of table in 26, which refers to your Division 2. Okay, so most of the things are passed on there. Okay. Then you have ASME. Okay. ASME is most widely used for thin bellows. Okay. Whomever vendor, if your bellow is designed by the vendor, because thin bellows are mostly designed by the vendor who are the manufacturer of it, they follow most of the time ASME. Okay. ASME covers the thin bellow design in very detail, and it's the most accepted method. Okay. But now many clients have started asking 4.19 also, or Appendix 26. So that is also an acceptable method, and it is also covering design in quite detail. So you can do that also, but most of the time it will be ASME. Okay, so 90% of the time you can say that it will be ASME. So now this was about information. Okay.
We're excited to bring you a comprehensive, one-day workshop on Bellowdesign that dives deep into critical aspects of designing both thin and thick bellows. Register now, with the link in the description below.